I am going to discuss the second order circuits. So in the previous two classes, first order with source, without source I discussed. First order linear network without source, that is source free and source circuits. So now in this second order circuits, first I am going to discuss source free. So RLC series circuit, here there is no source, and the current flowing through the IR, the current flowing through the resistor and current flowing through the inductor, current flowing through the capacitor is same, since the all three are connected in series. So I is equals to IR equals to IL is equals to IC. So next, similarly consider the parallel circuit, parallel RLC.
Yes, sir.
In the first order I considered only RL and RC, I think, right? So here for second order RLC you consider. So RLC series and RLC parallel, that means all the passive elements comes into picture. So this one parallel circuit also, this is also source free circuit.
This is LCR, no sir?
In here RLC, L, this is L. So here voltages are same. In the RLC series circuit, currents through the all the passive elements is same. Here the voltages across the passive elements all are same. So that is V. I am naming as V is equals to VR is equals to VL is equals to VC, and the currents are different. The current flowing through the resistor, current flowing through the inductor, current flowing through the capacitor, all are different values. Since all are connected in parallel, the voltages across the passive elements are same. The voltage across the resistor is same as inductor, is same as capacitor. So in the series circuit, current is same. The current flowing through the resistor, current flowing through the inductor, current flowing through the capacitor, all are same. So now I am writing the differential equation for these two circuits. So first I am considering RLC series circuit. So IL as the variable, IL as the choosing, IL is the variable, the current flowing through the inductor. So I am going to write the differential equation in terms of IL, so which will be a second order differential equation. How we will see it? So just apply, since all three are connected in series, so the voltage is nothing but additive. So VR plus, I am just applying KVL, VL plus VC is equals to 0. So what is VR? VR is equals to voltage drop across the resistor. So I am writing R into IL. Since IL I taken the variable. What is the voltage across the inductor? L into dIL by dt. So what is the voltage across the capacitor? You have to write the voltage across the capacitor in terms of IL.
Yes, sir.
I is equals to C into dV by dt. That is I, that is nothing but IL. The current flowing through the capacitor is, I am considering the IL. Since all are connected in series, so IL is equals to IC. So IL is equals to C into dVc by dt. So from this I have to write VC. So VC is equals to 1 by C integral minus infinite to tau, T,
IL of T dt.
IL of, since I am taking as dummy variable here, the integral limits are
IL of tau d tau.
infinite to T. So tau is the dummy variable. IL of tau into d tau is equals to 0.
Yes, sir.
So now I am differentiating this equation and dividing with L, the whole equation, right side and left side dividing with L and differentiating with respect to dt. So this term I am writing. So if you differentiate dIL by dt one more time, you will get second order. So d square IL by dt square. And I divided with the whole terms with the L. So L I divided. So next, this one first R into IL. If you differentiate one more time, R by L, since I am dividing with the L, dIL by dt. So here differentiation and integration will get cancelled. So here, since I am dividing this term also with L, 1 by LC IL. So this is the second order differential equation. Variable I chosen the variable is IL. So this is the second order differential equation in terms of IL. So this is the equation 1. So you have to solve these equations. So now I am telling how to write the expression, how to write a second order differential equation. Then I will teach you how to solve these second order differential equation. Now for the same circuit, RLC series circuit, if I choose the VC as a variable, here IL, the current flowing through the inductor, I chosen as a variable. So I got the second order differential equation in terms of IL. So if you solve this equation, you will get the IL of t. So similarly, for the same series circuit, if I choose the variable as the voltage across the capacitor, then R into VR. VR is nothing but I am writing R into IC plus VL. VL is equals to L into DIC by dt. Since the current all are connected in series, so the current flowing through the inductor is same as the current flowing through the capacitor is same as the current flowing through the resistor. So I am taking R into IC plus VC. VC write it as it is equals to 0. So same VR plus VL plus VC is equals to 0. This is the KVL equation. So VR is equals to R into IC, VL is equals to L into DIC by dt, and VC I didn't change, same. So now substitute, we already know the current flowing through the capacitor IC is equals to C into dVc by dt. So this formula I am substituting in the above equation. So now I am dividing with the L and dividing with the L, this equation, the above differential equation. So here if you substitute, IC is equals to C into dVc by dt. So I am dividing with the LC. So dividing with the whole differential equation with LC, both sides. So d square Vc by dt square.
Yes.
Correct. So this term I divided with the LC also, and IC, R into IC. So if we substitute C into dVc by dt here and dividing with RL, so plus C by L no, not C by L, right?
You're
C
dividing
by
by L and C, so it should be R should be in the numerator. So R divided by LC.
Correct. R by L, C
Yes.
get cancels, right? So R by L dVc by dt, and here also we are dividing with the 1 by LC. 1 by LC, Vc is equals to 0. Now the same circuit, for the same circuit, RLC series circuit, so one equation, second order differential equation, I written in terms of the inductor current, IL. So if you solve the equation 1, you will get IL of t. For the same circuit, IL of t. And for the same circuit, I written the second order differential equation in terms of the capacitor voltage. So if you solve the second equation, you will get Vc of t. Right? So if you compare these second order circuits or RLC series circuit with the first order circuit, in first order circuit, if you solve the first order circuit, only you will get only one parameter. But in second order circuits, here the parameters are two parameters, the current flowing through the inductor and the voltage across the capacitor. So since because of two parameters consist in the circuits, so we can write in two ways the differential equation, the second order differential equation, you can write in two ways by depending on the variable. So if you choose the variable as inductor current, I am getting the equation 1. For the same circuit, if I choose the capacitor voltage as a variable, then I am getting the equation 2 in terms of Vc.
Yes, sir.
Understood? So similarly for RLC parallel circuit. So similarly for RLC, so first I am writing the differential equation, then we'll see how to solve this. So similarly for RLC parallel circuit, so I am applying the KCL. So if you apply KCL, all the currents at the node, this is the node A, IR plus IL plus IC is equals to 0, right? Assume all the currents are leaving at node A. So what is IR? So I am writing first, I am choosing the variable as Vc first. The voltage across the capacitor, I chosen the variable. So I am writing the differential equation in terms of Vc. So IR, all the terms IR, IL, IC, write in terms of Vc. So since the variable I chosen as Vc, so IR is equals to Vc by R. Since the voltage across the resistor is nothing but voltage across the capacitor, both are same. So plus IL. So VL is equals to L into di by dt. So from this IL is equals to 1 by L integral minus infinite to t Vc of tau. So tau is the dummy variable. Vc of tau d tau plus, so I see the current flowing through the capacitor in terms of dVc, we can write it. This equation I am differentiating and dividing by C. Since here C is there, so I divide the whole equation right side and left side with the C. So I am differentiating one more time the above differential equation. So d square Vc by dt square this term, and I divided with the C. So here 1 by R Vc is there. If you differentiate 1 by R into dVc by dt, since I am dividing with the capacitor, so I mean capacitance value, so 1 by RC dVc by dt. So this is the term, and this term is nothing but if you differentiate, the integral and differential will get cancelled. Since I am dividing with the whole terms with the C, so 1 by LC Vc is equals to 0. So this is the equation 3. So for RLC parallel circuit, I chosen the variable the capacitor voltage, that is Vc. So the second order differential equation I written in terms of Vc. So for the same parallel circuit, if I chosen the IL as a variable, then so IR is nothing but VL by R and IL don't change, since I have to write the differential equation in terms of IL, and IC is equals to C into dVL by dt. Is equals to 0. So now substitute, we already know the voltage across the inductor V is equals to L into dIL by dt. So substitute this formula in the above differential equation and divide with the, so if you substitute here, d square IL by dt square comes. So d square IL by dt square. So and divide with the LC. LC, right? LC where I am dividing. Next.
D square IL by dt square, and then you have plus IL for
substitute. LL get cancels. 1 by RC.
1 by RC DIL by dt.
So the remaining term don't change, but we are dividing it to the 1 by LC. So 1 by LC IL is equals to 0.
Yes.
So 4 equations I got. So for each circuit I got 2 equations depending on the variable. So for the series circuit, 2 equations in terms of IL of t, in terms of VC of t. So similarly for parallel RLC circuit, in 2 differential equations in terms of VC and in terms of IL. So now how to solve these for source free second order differential equation? Since here there is no input, all the right hand side of the differential equations are 0. If you observe the 4 equations, all the right hand side of that all are equal to 0. So that means we can say these are all homogeneous differential equation. If the input is 0, then we can say that differential equation is nothing but homogeneous differential equation. Okay, how to solve the homogeneous differential equation? So generally I will explain, then we will go to the problem based on RLC, series or parallel, something like that. So general homogeneous differential equation, how to solve? So this is the, I am considering, is it visible? So I am considering general equation d square x by dt square plus b into dx by dt plus cx is equals to 0. So which is in the second order differential equation. Since here also there is no input, so homogeneous second order differential equation, this one is. So you leave it about d by d, differential term you leave it. So you have how to write a characteristic equation for the above differential equation. So d by dt is nothing but x. Substitute in the differential equation, d by dt is equals to
yes, I
x.
know this.
So here x square.
I know this method. Yes, sir.
You know this method? Okay, I am just fast, I will explain. So write the characteristic equation f square plus bx plus c. So this is the equation, characteristic equation. If you write the solution, so this is in the form of ax square plus bx plus c. Find out the roots. Minus b plus or minus b square minus 4ac by 2a. So if b square minus 4c, that is under the root, if it is greater than 0, you will get the roots are real and distinct roots. So if the roots get real and distinct roots, so this is nothing but over damped. I am just writing over damped. The response is over damped. So what is damping? I will explain. So if the real and distinct roots, that is b square minus 4c is greater than 0, so we are getting the real and distinct roots, different roots. So the response x of t is the response which is over damped response. So how to solve these? See here, k1 and k2 is unknowns. S1 and S2 is the roots of the characteristic equation. So S1, S2 you can substitute, that is e power S1t and e power S2t. But K1, K2 are the constants. How to find out these constants? So by using initial conditions. The initial conditions they will give in the problem. So considering that initial conditions, so solve the K1 and K2. So first I am considering the same, in the same solution x of t. So t is equals to 0 plus I am substituting. So K1 plus K2. So this is the equation 1. So I am differentiating x of t with respect to t, that is x dash of t. In x dash of t I am substituting 0 plus. So this is the equation 2. So solve these two equations, you will get the unknowns k1 and k2. So this is the way to find out the k1 and k2. Once k1 and k2 gets, just substitute in the response, that is x of t. So you will get the response. When over damped, when the system is over damped or when the equation is over damped, so you will get the response. So next one, b square minus 4c less than 0, then you will get the roots are distinct but complex. We are getting the different roots but complex. So this is the response equation is given. So this response is known as under damped response. Under damped. So this is the solution. So similar to that, how to find out the constants? Here the constants are k. A, B are the constants. How to find out? By considering the initial conditions. So first you substitute the same solution, t is equals to 0 plus. Differentiate this solution and substitute t is equals to 0 plus. So solve these two equations, you will get the unknowns. So last case, b square minus 4c is 0. If b square minus 4c is 0, then the roots you will get both are equal, real and equal. So this is the case, critically damped case. So this is case, critically damped case. So how to find out the unknowns? Here unknowns are k1 and k2, similar to the above two cases. So k1 and k2 you can get it by using initial conditions. So x of 0 plus and x of t you differentiate one time. So x dash of t you will get. So here in this x dash of t also substitute t is equals to 0 plus. So solve the two equations, two unknowns, you will get the unknowns k1 and k2. Okay. So this is the procedure to solve the second order differential equations. So just in written, I'll just steps. What are the steps to solve the second order differential equations? So these are the steps we have to follow to solve for the second order differential equations. This much of time.